This is ScoreBooster again this week with the concluding part of the atomic structure, because this topic is very important and we need to give it a very adequate attention, because the foundation of chemistry is actually built, or it's actually made of atomic structure. We have talked about other things, the structure of the atom, the models that support the structures, and briefly on the electronic configuration the other time. Today we are going to the energy level diagram, because actually studying the energy level diagram will make us to understand the chemical reactions and bonding, to show where electrons are being used, and the prediction of bonding type, which I think they are the building blocks as far as chemistry is concerned. The learning objective at the end of this lecture, it is expected that students should have understood the description of the energy level of elements, particularly the first few elements, let's say the first few 20 elements or 30 as the case may be, if the atomic number is known, because that is the most important thing in writing the electronic configuration and the energy level of each of the cells in the element. Students should be able to draw energy level diagram and write the electronic configuration of the element, as I've said earlier on. If we know the atomic number of the element and the electronic charge of it, if it's carrying charge or not, so we can actually write the electronic configuration, because that would determine the number of electrons the element actually is carrying. Then students should have understood the concept of valence electrons. It is very important as far as chemical bonding is concerned, although chemical bonding is still a far topic, but we need to get some knowledge of it before we actually get there. The students should be able to describe the concept of isotopy, isotope, and give examples, ions and radicals. This is the energy level diagram. This is the nucleus. Let us show the half of the nucleus. This is the center nucleus. Then there are shells surrounding it, as we have proved the other time. So this is the 1s, the first shell that contains only one orbital, s orbital. This is the second shell that contains two orbitals, 2s and 2p. This is the third, 3s, 3p and 3d. This is the fourth. So this first one, as we have said the other time, has a principal quantum number of 1, and the principal quantum number determines the energy and the distance to the nucleus. As the number is increasing from 1 to 2 to 3 to 4 to 5, the energy is increasing, which means cell 2 has a higher energy than cell 1, cell 3 has a higher energy than cell 2, like that. And again, if we have degeneracy in a particular shell, when we have subshells, like we have P that has 3 subshells, the PX, the PY and the PZ. P has a higher energy than S. D has a higher energy than P. Although this is just a few of the shells, there are many subshells that we can have. We can have F, we can have G, like that. And if needs arise, the chemist can create another ones. But as far as our level is concerned, I think this is just what we need. So 1x is the closest to the nucleus, rather. 2x and 2p they are the next, 3, then 4, like that. So 2p is having a higher energy than 2x, 3p is having a higher energy than 3p, 3d is having a higher energy than 3p. But it is surprising that 3d has a higher energy than 4s, because that is actually what is being obtainable in nature, although chemists they are still proving it. It is beyond the scope of discourse. But what we need to understand now is that we have 1s, 2s and 2p, then like that. So the principles of filling orbitals with electrons, because we cannot just jump, say because we want to fill electrons into all these orbitals, we now start from 5. No, because the electron with the lowest energy occupies the shell with the lowest energy. So the level of energy of electron determines the particular shell the electron will occupy. That is what we learn about what Niels Bohr talked the other time. So, and in doing that, we have some principles that guide the filling of orbitals with electrons. The first one is the Pauli exclusion principle. The second one, the Bohr principle, and the third one is the Ohm's rule. The three are equally important, and students need to know them often and apply them all the time, because it is very rare that the three of them will not be applied together. Majority of the times, the three of them will be applied at the same time to the same problem. The Pauli exclusion principle is that it is certain that we can't have two electrons behaving the same manner, even if every other properties like magnetic quantum number, principal quantum number, asymptotic quantum number, even if they are the same. What this principle is trying to tell us is that they cannot have the same spin. One should be spinning in the clockwise direction, the other one is anti-clockwise. That is the plus half and the minus half we talked about in video 3. The Bohr principle is that the electrons fill the lowest energy shell before going to the orbitals of higher energies. That is reasonable enough, because the level of energy of a shell of electron determines the shell it occupies. So if a cell is having a lower energy, definitely it must contain electrons of a very low energy. If the energy of electron increases, the electron jump from the orbital of low energy to orbital of higher energy. We are still going to that later. Ohm's rule is that electrons are filled singly before pairing takes place. This happens in in orbitals that we have subshells, like in P, like in D, like in F. It doesn't happen in S, because S is just only 1. If it is 1s, it's 1s. If it is 2s, it's 2x. But for P, we have degeneracy, px, py, and pz. If it is D, we have D into 5 places, dxy, dx square, y square, dy square, x square, like that. They have 5. So if, let us assume that we have electrons to be filled into this 2p. So we have to fill each one into each block first, singly. So if there are more electrons, then we now start from anywhere before pairing out takes place. It is not that we put 2 in the first one, like let's say px, now put the rest in py and pz. No. This is the chart that shows the energy according to how we be going if we are to fill electrons into shells. But we need to note that the lowest vacant orbitals are filled first, like 1s now. We start from 1s, then to 2s, 2p, 3s, 3p, 4x, 3d, 4p, 5s, like that. So we follow the direction of the arrows. In the case where there are more subshell at a particular energy level, each of the subshell are filled singly first before pairing takes place. If there are more electrons, that is the condition. If there are more electrons, because it is not compulsory that we have to fill all the subshell we have to pair them, but the most important thing is that they must be filled singly first. Then, if we have more electrons, then we pair the subshells. So let us now take an example. Let's use oxygen that has 8 electrons. We know from lecture 3 that each of these orbitals can contain 2 electrons. S can contain 2, Px contain 2, Py contain 2, Pz contain 2, dx square y square contain 2, like that. So if we now have 8 electrons, the closest to the nucleus, since there is no degeneracy, this is 1s. So we have up and down. So every other things are the same in this first one, but the spin are not the same. So which satisfy the Pauli exclusion principle of filling the orbitals with electrons. So we have 6 more electrons. So we go to the orbital of the next energy, that is 2x. So there's no degeneracy. Also, we fill it with 2 electrons of opposite spin. Clockwise is up, then anti-clockwise is down. There's no rule regarding this. You can put this down first and up second. Just make sure the 2 are not facing up or facing down at the same time. So after 2x, so we still have 4 electrons. So we go to the other one, 2p. So we are following Pauli exclusion principle and Aufbau principle. The Pauli exclusion principle is that even if every other thing remains the same, the electrons must have opposite spin. That is what we have fulfilled here and here. The Aufbau principle is that the electron occupies the orbital of lower energy before orbital of higher energy. So we have filled 1s before 2s. And in this shell 2 now, we have filled 2s before 2p. Now let us now go into the Hooke's rule. Electrons are filled into orbitals singly before pairing takes place. So we have 4 more electrons. So we have to fill each one with one electron first. 1, all of them are opening up, they are facing up. 2, 3. So now we have 1 more electron. So we can put it anywhere. I just decided to put it here. Somebody can put his own here. Somebody can put his own here. There is no rule regarding that. We just make sure that the 2 of them are not facing up, or the 2 of them are not facing down. And we don't put this one here, and this one will now become vacant. No, because we have to make sure every subset is filled singly first, then before we now pair it. So by so doing, we have followed the 3 principles that must be followed if the correct electronic configuration for any element is to be written. So going to the concept of electronic configuration properly. Electronic configuration is an alternative and a better way of representing the energy level diagram of an element, because as we have seen, this one is too cumbersome. So we need to get a more scientific and a brief way of representing the same information that we have put here. That is what we want to do with electronic configuration. It is an elegant way of representing the structure of electrons in an element, as I've said. Let us now do the examples. For oxygen that we have done here, let us now repeat it here. We should not forget that we have to start with 1s. This is 1s. S contains 2, as it's containing 2 here. Then we go to 2s, as we have here. 2s contains 2 also. 2s contains 2 also. Then after 2s we have 2p. So that's what we have done here. 4 electrons. So 4 electrons. So we write all the 4 together because we don't need to split them into px, py, and pz here. We can just put it as p4. And again, p can contain a maximum of 6 electrons because of the generation into 3. Each of them can contain 2. So we can put 4 here. And then being there are more, after filling this 1s and 2x, there are more than 6 electrons. So we go to another energy level, not 2p again. So let us now do this with chlorine. Chlorine has 17 electrons. 1x as usual, 2 electrons, 2x usual 2 electrons. So after filling 4, we still have 13 more electrons. So we can just put 6 here because p can contain 6. After 2p now, so we can go to 3x. We should not forget that x contains 2. It is immaterial whether it is 1x or 2x or 6s. S must contain 2, at most 2. It can contain 1 if you are writing only 1 electron, but it cannot contain more than 2. So we put 2 here. So remaining 5. So the 5 that remains now. So after 3p, after 3x, so we go to 3p. So we just put the whole 5 here because it's not up to 6. So the same thing with iron. 1s2, 2x2, 2p6, 3s2, 3p6, 4x2. So after this we have 20 electrons. And iron is 26, so the other 6 can be put here, 3d, because 3d after 4x. We should note that the sum of the superscript numbers equals the number of electrons. If we count all the superscript, 4, 2, and 2, so making 8. If we add them together, making 8, it's equal to the number of electrons in oxygen, neutral oxygen, 8. 17 is chlorine, 26 is iron. So we now go to the concept of valence electrons. What is valence electron? These are electrons in the outermost energy levels in an atom. The outermost energy level in an atom. Energy level is also called shell. So when we have the remaining shell in an atom, it is only in, I think, in hydrogen and helium that we have only one shell. So other elements, we have more than one shell. So definitely one must be more outer than the other. So in such a case, so we can have valence electrons. And in hydrogen and helium that we have said that contain only one energy level, so that energy level is the outermost energy level. So if we take oxygen as an example now, 1s2, 2s2, 2p, 4. We should not be confused because this 2p is the last thing we are writing here. No, this 2 means they belong to the same shell, to the same energy level. It is because of the difference in the principal quantum number which gives rise to the difference, the degeneracy of the orbitals that we are seeing 2s and 2p. These 2s and 2p constitute what is called the outermost energy level for oxygen. So to get the valence electron here, we need to add this electron 2 plus 4, making 6. We should not mistaken adding these 2. We need only the superscript, the indices here. They are the one we are adding, making 6 electron as the valence electron for oxygen. So exercise now. Determine the number of valence electrons in the following element. Chlorine, this is the electron configuration for chlorine, this is for iron. So now, considering chlorine, we have 3x and 3p. The third shell is the outermost shell, that's the outermost energy. and it contains 7 electrons, 2 plus 5. So for chlorine, we are having valence electron of 7 because the outer shell is equal to 3, the third shell 3s and 3p. For iron here, this is 3d. We should not just go to 4 because 4 is greater than 3. No, the outer shell is 3d. So the outermost shell is 3, which has 6 electrons. Although we later in the course, by the grace of God, we study the group to which our ion belongs to. Not only ions in this group, we call them transition metals. Not only ions, we have some other elements that are in this group. So we are going to the concept of isotope now. What is isotope? What is isotopy? Isotope just means very neutrons, but scientifically and properly said, let's determine isotopy first. There is a phenomenon that is responsible for this. So isotopy is the phenomenon whereby atoms of the same element have the same atomic number but different mass number. We should not forget that the mass number is the total mass in the nucleus, which is the addition of the proton and the neutron. And for a neutral element, the proton and electrons are equal, which means if we have two elements, the same element in two forms that have the same proton number but the mass number are different, it means that the neutron content is different. So that phenomenon that is responsible for disparity in the number of neutrons is what is called isotopy. So the isotopes are just the atoms that have that isotopy phenomenon. So those atoms of the same element, they must be the same element with different number of neutrons. That's a different mass number. Let us now take hydrogen as an example now. There are many elements like that. We have argon, we have carbon, we have carbon 3, we have hydrogen 3 also, argon 2, like that, etc. This is hydrogen. The same hydrogen is presented itself in another form, then another form again. This one has no neutron because the mass number is 1, the atomic number is 1. If you subtract 1 from 1, you get number of neutrons, as we have done in video 2. So we're going to get 0. This one has no neutron. This one is having 1 neutron now. 2 minus 1. This one is having 2 neutrons. So we can see that in these 3 forms, we have very number of neutrons from 0 up to 2. And it's the same hydrogen because of the atomic number 1. There's no any other element that is having atomic number 1. So it is only hydrogen, which means that they are isotopes of each other. Exercise. Student has to list the 4 other elements which exhibit isotopy apart from the 2 above. And we should note that for correct calculation of atomic mass of an element, weighted average is used. These are the atomic masses of hydrogen. This is 1, 2, and 3. But in actual sense, they are not whole number. They are something like decimal. There are decimal points after these whole numbers. This is because of the weighted average. What is weighted average? The average that is calculated after considering the relative abundance of each of these constituents in nature, because they are not the same in nature. Some is very rare, some is maybe this one is very rare, maybe this one is the most commonest one among the 3. So to now calculate the relative atomic mass of hydrogen, because we can't be using 3 for our calculation, so we need to generalize on 1. And if we take 1, it is like we are disregarding the other 2. So we have to take into consideration the amount of each of them. It is like it's a civil engineer finding the mass of aggregate, sand plus water plus stones, other rocks. We can take the mass of the water as the mass of the composite, or the mass of the sand alone as the mass of the composite, or the mass of the rocks, the stones alone as the mass of the composite. We have to consider the contribution of each of them, which one is more, which one is least. So that will now give us the greatest insight into how heavy the substance will be. It makes the atomic masses of most elements not to be whole numbers, like we have hydrogen 1.0079 atomic mass unit. Don't forget atomic mass unit, we have explained it in lecture 3 before. 1.009 means this is 1, this is 2, this is 3, and we can see 1.0079, it's closer to 1. It means this one is relatively more, far more abundant than the other ones. Examples. This is question 10, 1987. An element X, an hypothetical element Z, contain 90% 16.8, 10% 18.8. Then we have to find the relative atomic mass. We should not forget what we said about the weighted average, that we have to consider the relative abundance of each of them. This is how to do it. This is the 90% of this. We multiply them together. The 10% of this, we multiply them together, and we add them together, then we divide it by 100 because it is percentage. Or you can say 0.9, 90% multiply 0.9 by 16, or plus 0.1 by 18. So anyone, it is mathematics, anyone, we are going to arrive at the same answer. And by doing that, we have 16.2, option B. And we can see it is not whole number. Definitely A and C cannot be the answer because of this 0.0. So that is how to eliminate wrong answers. A metallic ion, this hypothetical ion with 2 plus, with an inert gas structure, contains 18 electrons. How many protons are there in this ion? Question 9, 1988. The question says, this ion, a X2 plus, this is a dimetallic element, is having an inert gas structure. What is inert gas structure? It means the shell is complete. Contains 18 electrons. Because 18 electrons is an inert gas structure. So inert gas actually contain 18. One of them contain 18 electrons, like 2, like 8, like 18, like that. How many protons are there? This one, as it is now, is having 18 electrons. So had it been there is no plus, what would be the number of protons? So and there is plus now. If there is no plus now, so we'll have add 18 protons also, because when we have the balance 0 on top, we have 18 electrons, 18 protons. But now that we are having plus and 18 is a negative, there's one other number, a positive number greater than 18, such that if you remove 18 from it, you are going to get 2. What is that number? It is 18 plus 2, that is 20. Option A. Proton is unaffected by the loss or gain electrons. Loss or gain of electron. Even if it loses 1 million electrons, proton is unaffected. Another example is this. How many valence electrons are contained in the element represented by this? In determining the valence electrons, we are not interested in the mass number. It is only in the atomic number here, and since it is neutral, so the number of electrons and the number of protons are equal. So now 15. So we write the electronic configuration now: 1s2, 2s2, 2p6, 3s2, and 3p3. So the outer shell is 3, shell 3, that contains 2 plus 3 electrons, making 5. So option B is the answer to this problem. Had it been is 16 now, we can just put 3p4 here and we add 2 plus 4. So if it's more than that, so we continue writing the element. If it's less than that, we truncate it to where the electron is. We don't need to create electrons by ourselves. We don't need to change the electrons. We only need to write it according to the 3 principles that we have highlighted before. Ions. What are ions? The ions are just elements that are carrying charges. If it is positive charge, we have cation. If it is negative charge, we have anions. So when we now have 2 elements that are having the same electronic structure, but they are different elements, both are called isoelectronic. Like we have chlorine minus and argon. When chlorine gain electron, it has 18 electrons. So argon ordinarily it is having 18 electrons. So since chlorine and argon, chloride ion and argon element, they are carrying this. They are having the same number of electrons, but they are different elements. We call them isoelectronic. And again, it is not only elements that carry charge. A group of elements like this, like ammonium, like nitrate, like phosphate, like sulfate, etc. You can carry charges, and they are called radicals. Single elements are called ions. These ones are called radicals. When we have group of elements carrying a single charge and behaving as a single unit like this. Charges are brought about as a result of transfer of electrons. It is either gaining an electron or losing of electron. If it is gaining electron, we have anions, negative. If it is losing electron, we have cations, positive. In summary, energy level diagrams are used to describe the electronic structure of the element. The electronic configuration is a less bulky way of writing the electronic structure of atoms instead of energy level. The Pauli-exclusion principle, Avro principle, and Untitled are the rules of writing the electronic structure of elements. 1s followed by 2s followed by 2p up to 3d etc. is a sequence for writing the electronic configuration of the element based on the rules above. Valence electron is the total number of electrons in the outermost shell of the atom. Isotopes are atoms of the same element having the same atomic number but different mass number. Ions are atoms that carry charge. Group of elements that carry charge are called radical. It is my hope that following what we have discussed, these exercises should come like a bonus to every one of us. So these are just 7 problems, and after doing the 7 problems, these are the answers. So we can actually check if we are right or wrong. Thank you for listening. God bless you. And don't forget to like and share this video.